Hello, my name is Tao Lin. I'm currently a postdoc at Microsoft Research, and I will join CUHK Shenzhen as an assistant professor next month. I will talk about our work on information design with large language models. This is joint work with Safwan, Paul, Renato, Sai, iPhone, and Song. This is a EC 2026 paper. Information design is an economic scenario where one player, usually called sender, strategically reveals information to influence the decision of another player, usually called receiver. A typical example is advertising, where the seller of a product strategically reveals information about the product to increase the probability that a consumer buys the product. People have estimated that uh, one quarter or even 30% of the US GDP comes from persuasion, and persuasion is a form of information design. Since there are many potential applications of information design, non-surprisingly, there are also many economic models about information design. So people have proposed many mathematical models to study information design and more general communication games as well. Today, we will focus on this Bayesian persuasion model proposed by Gematica and Gensko in 2011. Among all of these classical economic models, there's a common assumption, and this is a Bayesian assumption. In those classical models, it is assumed that the information transmitted from the sender to the receiver is a random variable correlated with some state of the world. So we have a random variable called the state of the world distributed according to some prior distribution, mu0. Then the sender sends a signal to the receiver. The signal is a random variable correlated with the state of the world. The receiver does base update after receiving the signal. So they form a posterior belief about the state given the signal. And then the receiver takes some best responding action. Importantly, in this model, how the signal is communicated doesn't matter. All that matters in this model is the correlation between the signal and the state of the world. Only the correlation between them determines how the receiver behaves. But we know that in practice, real-world decision makers are often affected by the framing of information. So receivers in practice may be affected by how the information is transmitted. Let me talk about some examples. The first example is this well-known framing effect. Suppose I am describing an investment plan. I can describe the investment plan in two ways. I can say that it has a 90% chance of success, or it may fail with 60% probability. I am describing the same information, but in different ways. And this different framing creates different perception in the receiver's mind. Another example is advertising, where we are designing a slogan or logo of a line of products. So I may use a logo that says feel the power or says naturally better. And these different slogans create different perceptions. So I am describing the same line of products, but describing them in different ways. And these different ways changes the consumer's feeling about the line of products, but it actually doesn't convey any fact about the products. Motivated by the previous examples, our work aims to incorporate framing effect, which is a non-Bayesian effect, into classical information design models. Here are our contributions. Our first contribution is that we propose a theoretical model for Bayesian persuasion with framing effect. So we incorporate framing effect into classical Bayesian persuasion model. Under this model, we study two optimization problems where we optimize framing. So one problem is framing only optimization, and the other is framing signaling joint optimization. Our second contribution is that we demonstrate the ability of large language models to simulate real-world framing effect as well as optimize framing. Let me talk about the first contribution, which is a theoretical model for Bayesian persuasion with framing effect. In this theoretical model, we have two players, a sender and a receiver. There's a state of the world, which is a random variable distributed according to some prior distribution. We assume that the sender knows the prior distribution. The sender chooses a framing, little c, from a set of framings, capital C. Importantly, the sender chooses the framing without knowing the realization of the state of the world. Although the framing is unrelated to the state of the world, it still affects the receiver's belief. So we say that the framing shapes the receiver's subjective prior belief about the state of the world to some distribution mu c. This mu c is uh, determined by the framing. And this mapping from the framing to the subjective prior belief of the receiver is called a framing to belief mapping. Now the sender has a correct prior belief mu0 about the state of the world. The receiver has a subjective, possibly wrong prior belief about the state of the world, mu c. Then a standard Bayesian persuasion game happens. The sender designs a signaling scheme that maps the state of the world to a distribution over signals. So it sends the signals, the, condition according to the signaling scheme, conditioning on the state. Given the signal, the receiver obtains posterior belief, and this posterior belief is obtained by Bayes update from the subjective prior belief that the receiver had in the first stage, and this subjective prior belief is induced by the framing. After forming the posterior belief, the receiver will choose an optimal action, optimal according to their utility function. Then the receiver's action, as well as the state of the world, will determine the sender's utility. Sender's utility function can be different from the receiver's utility function. You can think of the framing as a context. So it is chosen independent of the state. So it doesn't depend on the state. However, it still affects the receiver's prior belief about the state. And this is a non-Bayesian effect. Let me go back to the advertising example. In the advertising example, the sender is the clothing brand. The receiver is the consumer. And we have four possible states of the world. So each product may be fashionable or functional, and durable versus not durable. So we have four combinations. The receiver has three actions: buy the product on sale, buy at regular price, or not buy. Now, what is the framing? The framing here is a product independent description about the product line as well as a slogan. So I am designing a slogan for the line of product, and also I am giving you some generic description about the line of product. So I am not giving you specific information about each product in this product line. And the product specific information is given by the signaling scheme. So, so a signaling scheme it maps the state of the product to some signal. It could be advertisement with discount, advertisement without discount, or no discount. No, sorry, no advertisement. Okay. Under this theoretical model, we study two optimization problems. The first optimization problem is framing-only optimization, where we fix the signaling scheme and then optimize the framing. And we aim to optimize the expected utility of the sender, assuming that the receiver best responds according to their posterior belief formed by updated from the subjective prior belief. The second problem is joint optimization, where we optimize the framing as well as the signaling scheme, and we still maximize the sender's utility. Instead of optimizing the framing, we can actually do a theoretical simplification to say that we can directly optimize the subjective prior belief of the receiver. So we assume that the framing to belief mapping, this L, can be perfectly simulated. For example, it might be simulated by a large language model. So now, because this framing to belief mapping can be perfectly simulated, we have the access to this set of B, which is the set of all prior belief that can possibly be induced by the framings. So I enumerate all the framing in this set, and then I consider the corresponding subjective prior belief that is induced by the framing. And I assume that this set B is given. Now, the reason why I'm describing this theoretical simplification is that the set of framing is the set of natural language sentences, and that's not easy to optimize over. But instead, the set of prior belief is a subset of probability simplex, and it can be mathematically optimized. Now, under this reformulation, we can write the optimization problem as optimization problem over the set B. Now, let me talk about our theoretical results. The first theoretical result is a computational complexity result, where we show that both the framing-only optimization and the joint optimization problems are NP-hard. In particular, for the first problem, we show that for some fixed signaling scheme, computing the optimal framing, or equivalently computing the optimal prior, is NP-hard. And the problem is NP-hard even when I can induce all possible prior beliefs in the entire probability simplex. The second problem the second result is about joint optimization, where we show that computing the optimal pair of prior and signaling scheme is NP-hard. And this holds for some simple strict subset of the probability simplex. Here are the proof sketch. For the first result, we prove the first result by a reduction from the Bayesian-Steigelberg game. In the Bayesian-Steigelberg game, we have a leader and a follower. The follower has a private type. We show that framing only optimization problem is equivalent to Bayesian-Steigelberg game in the sense that the subjective prior belief we are optimizing corresponds to the leader strategy in Bayesian-Steigelberg game, and the signal we send corresponds to the type of the follower. Because Bayesian-Steigelberg game is known to be NP-hard, our framing-only optimization problem is also NP-hard. For the second result, we prove the NP-hardness by a reduction from independent set. Our second theoretical result is a continuity result, where we want to know whether the two optimization problems are continuous. In particular, we look at the sender's objective function, which is the sender's expected utility when the sender's induced subjective prior belief of the receiver to be mu, and it uses signaling scheme pi. So this is a function of these two optimization variables, mu and pi. We notice that we prove that when we fix the signaling scheme pi and we optimized over mu, this objective function is discontinuous in mu. So when we change the framing a little bit, it may change. It only change the prior a little bit. It changed the posterior a little bit. However, that can cause a sudden change in the receiver's action, and as a result, cause a very large change in the sender's utility. So the objective function is not continuous in mu. However, if we optimize pi as well, then the objective value is continuous with respect to mu. So we fix the mu, optimize the pi, and then look at the optimize the objective value. This is actually continuous in mu. Then if we optimize mu, then we have a continuous optimization problem. This suggests that joint optimization might be more tractable than framing-only optimization. Although both problems are NP-hard, joint optimization might be easier than framing-only optimization in practice. Let me then talk about the second part of our contributions, which is about using language models to simulate real-world framing effect and optimize framing. Let me show you the experiment pipeline, where we use language models to do framing signaling of joint optimization. As I said, we use language model to simulate the framing to belief mapping as well as optimize framing. Here's our theoretical experiment pipeline. We have three large language models. The middle one is a generator that generates framing. After it generates a framing, we give this framing to another large language model to estimate the prior belief that the receiver will have given this framing. So this is denoted by mu hat of C. Then we give this mu hat of C to an analytical solver to solve for the optimal signaling scheme associated with that estimated prior belief. And then this allows us to compute the expected utility of the sender, and we provide this utility back to the generator. There's another language model that checks whether the framing is sound. So it needs to be consistent with facts. So the language model cannot hallucinate things. We provide the soundness score also back to the generator LLM. And then we ask the generator LLM to improve the framing. So we are doing some iterative prompt optimization here. Going back to the advertising example, this means that we are trying to optimize the slogan and description of the product line. And we have an analytical solver to find the optimal signaling strategy. In addition to these components, we also have some consumer description. So these are not framing. These are some information about the consumer. For example, these are fashion-aware consumers, and they are not deeply familiar with technical characteristics. And we provide this consumer information to all of those LLM components. Now, here's our first experiment result. We use LLM to simulate a framing to belief mapping. So we provide a framing to GPT, Claude, as well as some human subjects, and then ask what's their belief about the product. We asked what's their belief that a product from the product line is chic and durable, chic not durable, functional durable, or functional non-durable. So these probability should sum to 1. And then we look at the GPT response as well as human response, and we found that they are actually quite consistent. Okay. This suggests that LLM does has the ability to simulate the framing to belief mapping. Our second result is to use LLM to optimize the framing. As I said, this is the iterative process. So we obtain this graph where the horizontal line is the number of iterations and the vertical line is the utility times the soundness scored. And we see that the performance increases over time. Here are some examples of framings generated by the LLM. For example, GPT finds a framing that uses less technical terms than the original framing it begins with. You can pause the video here to take a look at this text. And we also tried Claude, and turns out that Claude generates a much more interesting slogan than the original slogan. And also Claude completely avoids the technical terms. Let me summarize. We propose a theoretical model that incorporates framing effect into a classical Bayesian persuasion model. We show that both framing only and joint optimization problems are hard, but joint optimization might be easier in practice because it is continuous. We also demonstrate LLM's ability to simulate real-world framing effect and optimize framing. Our work is just one initial attempt to bridge classical information design theory with real-world persuasion, and we bridged these two using recent LLM technologies. We are not the only person who are doing this line of work. There are also some other works using language model to do Bayesian persuasion.